All right, everybody, let's finish this up. We're going to be finishing up our fundamental theorem of calculus. So we're going to be doing our fundamental theorem of calculus for divergences. Okay, that's what we're doing right now. All right, so this is a really, really special property of divergences that is super useful, and it has, in fact, it has 3 different names. It's so useful, and it looks like this. It's the integral over a volume of a divergence of a vector field, like our V, okay, over, so you're integrating over d tau, the volume, right? So you're integrating over like the inside of a sphere or something, right? Is equal to the integral over the surface of that sphere, or whatever volume it is, of the vector field dotted in with dA, okay? So this is super, super important. And let me point out here that this here is the boundary term, right? Because this surface, that's what that means, closed surface, dA, right? You're integrating over the surface area now. Is a surface, not just any surface, that bounds the volume that was in the other integral, okay? All right, well, let's do an example, and I'm going to tell you what this is called first. It is called, the 3 names it has is Gauss's theorem, and this is directly related to Gauss's law. You might recognize that with, this is a flux integral, right? A flux through a closed surface. Or law, okay? Okay, and it's also called Green's theorem. You'll see that more in sort of when you get into, mathematical methods of physics. It's called Green's more often. And it's also called the divergence theorem. Okay, all right, let's do an example. So we are going to, let's look at, let's see. We had our cube, if you remember, our cube, and we said that I can't remember, it looks like, oh yeah, I think I may have told you the wrong, do you remember when we did a cube, we did the flux through all the faces, and I just said they add up to 16. I think it was 20 now that I'm looking at it. Anyway, we didn't do all the sides, so we didn't actually prove to ourselves what it was. But anyway, okay. So well, we did have a cube, and let me go back and take a look at what that looked like again. Okay. And I'm terrible at drawing cubes, but I will try. Now and I would like a little thicker pen, so give me a second here. Where's my pen thing coming up? Huh, hold on. Give me 1 second. I am going to try to find where my pen thickness is coming up. Doesn't seem to be working. All right, give me a second. I think I'll pause and just come back because I can't deal with this pen. Okay, well, something's wrong with my drawing program. I can't change the pens. Anyway, okay, let's get back. Let's try to make our cube. Let's make it in this color. So let's see. I'm terrible at drawing cubes. Let me see if I have one to look at. There we go. All right. So we're going to come out here. There's one side. And then we have another side. And yeah, this is the worst cube known to mankind. Okay. Sorry about that. It looks almost like a rectangle. It really shouldn't. Okay. All right. And this is the z-axis. the y-axis and the x-axis. So this was our cube, and like I said, I think I screwed up the total flux. To remember that we calculated the integral around this whole surface of v dot dA before, okay? And we should have gotten 20. We didn't actually go through all the sides, FYI. It's a good exercise for you. And now what we're going to do is going to look at this side. Okay, so let's do it. Let me write down what V was. Okay, so what was V? So our V, our vector field for this case, was 2xz in the x hat direction, plus x plus 2 in the y hat direction, that's a 2, plus y z squared minus 3 in the z hat direction. Okay, so we want del dot v, right? Because what we'd like to do is calculate this integral and make sure it's the same as that, which we got 20, right? So we got 20 for this one. So again, I didn't actually calculate that, but okay. So del dot v is, remember, del is x hat del x plus y hat del y plus z hat del z. And then we're dotting that with our y, our v, v. There's 2xz x hat plus x plus 2 y hat plus y z squared minus 3 z hat. I still need to learn how to write straight on this. Okay. So the dot product means that the x derivative acts on the x component, so 2xz, and then we have the y derivative acting on the y component, which is x plus 2. And then we have the z derivative acting on the z component, which is y z squared minus 3. Okay, all right, and this is a scalar, this del dot v. Okay, so let's actually do the derivative. So here, the derivative with respect to x is just 2z. And then we have plus the derivative with respect to y of all this, which is 0, because there's no y's in there. The derivative with respect to z is just y times 2z. Okay, and there you go. So we have the total one is 2z 1 plus y. Okay, all right. So let's see, now we want to actually do the integral over the volume of this cube, okay? So, and of course it doesn't look like a cube, but it is, okay. And the side length on these, which I didn't write down here, is 2, right? And 2 and 2, okay? So we're going to be integrating our del dot v d tau. Remember, d tau is always dx, dy, dz in Cartesian coordinates. So we have the integral 0 to 2 dx. And since there's no x's, that'll just be by itself. And then there'll be the integral of 0 to 2 1 plus y dy, and then the integral 0 to 2 of 2z, okay, dz, okay, because d tau, right, d tau is dx dy dz. All right, let's do the integral. So we have this one here, the x integral is going to be x from 0 to 2, and that's just going to be 2. And then we have 1 plus y is going to be y plus y squared over 2 between 0 and 2. And so that's going to be 2 plus 2, which is 4. And then we have the integral of 2z. That's going to be 2z squared over 2 from 0 to 2. So that's just going to be 4, okay, because the 2's cancel, right? So this is 4. So we get 4 times 4 times 2. So why am I not getting 20? Oh, why did I think it was? Oh, I am messing up all left and right. I just read the wrong line. Oh, come on. Okay. 2 times 4, which is 8 times 4. I feel like we're missing I feel like we're missing a factor of 2 somewhere. Let me see. Yeah, well, I screwed this up. So this is, here's an extra credit problem. So figure out what's going on here, because this is going to be 24, right? No, it's not going to fuck 24. Not doing good today. Okay. So we have 8 times 4, which is 32. Okay, now your job is to figure out what went wrong here. So I think this is right. I think this calculation is correct, but you should check this calculation. And then what you should go back and do, okay? Go back and calculate. Remember the example we were doing with the faces of the cube? Go back and calculate this guy here, okay? I said it was 20. It's not going to be 20. It should be 32 unless this calculation is wrong. Okay. Extra credit. A chunk of extra credit too. I'm going to give you a lot for figuring this out. So figure out if I did something wrong here, and I'm going to double check right now. Let's just go back. So I'm going to make sure that I wrote down the function correctly. Okay, we have 2xz, yes. X plus 2, yes. Y times z squared minus 3, yes. Okay, we're good on that. The derivatives, let's see. This will be 2z, that is correct. Yeah, 2z, yes. Okay, this one will be 0, okay. And this one here will be 2z times y, right? Because if we multiply this out, we'll get y times z squared minus 3y. That's not going to have a derivative with respect to z. Okay, so I think that's all right. And then this gives me 1 plus 2z times 1 plus y. Then I have the integral dx, dy, dz. Yes, this gives me x, which will give me 2. This gives me y plus y squared over 2, which will give me a 2 here, a 4 here, over 2. So it gives me 4. And then this cancels out, and this will give me 4. 4 times 4, 16 times 2, 32. I think that's right. You should double check now that I've you should triple check now that I've double checked, and then go back in your notes, and it's also in the book, right? That in the book they calculate only 5 of the sides. They calculate the flux through 5 sides of the cube, not all 6. So why don't you go back and look at all that and see where you can figure out where it should be 32, because these two integrals are the same. Okay. Anyway, all right, let's move on. We're moving on from that. Okay, disaster area. Okay. All right, let me kill this layer so you don't need to see it anymore and go to the next one, because we're on to the fundamental theorem. So the fundamental theorem of calculus for curls. Okay, fundamental for curls. Let me go to my page. Okay. Fundamental theorem for curls is there. It has a special name as well called Stokes' theorem. And it looks like this. You have an integral over a surface, okay? And in this case, it's not a closed surface, okay? Of the curl of a vector field dotted in with dA. So remember, the curl of a vector field is the vector itself. So that vector dotted with dA is equal to the closed path integral of v dot dl, right? Okay. So remember, this is the boundary term now. This is the boundary because a curve is a boundary of a surface. So if I have some surface here that I'm shading in a little surface. Okay. And now the boundary to that surface is going to be this, right? When I draw around it, it's a curve, a closed curve that's a boundary of that surface. Okay. Think of a bubble. I'm sorry, think of some soap when you have a bubble machine, or not a bubble machine, but one of those things you put in a little jar of soap and water and you pull it out and you're about to blow a bubble, right? The ring of that little bubble maker is the bounding curve, right? So that little bubble maker looks like this, the bounding curve, and then the sheen of that film of soap that you're about to blow a bubble with is the surface, right? Okay. So that's the idea behind this. And here, this is on that path, and this P, right? P is the bounding path of, or curve of surface S, okay? Now, remember, it can't be a closed surface because then there would be no path, right? What path bounds the surface of a sphere? There's no path that bounds that, right? It has to be an open surface. Okay, this is an open surface, not closed. But the similar, all of these fundamental fundamental theorems of calculus have a similar flavor, right? They're the integral of a derivative is equal to the boundary, right? So boundary of whatever is being integrated over. Okay. All right. So let's see. Give me a second. So let's go to page 3. Let's do an example. Okay. So let's do an example here. So our example, we have a vector field that looks like this: 2xz plus 3y squared in the y hat direction, plus 4yz squared in the z hat direction. And we want to check Stokes' theorem. Okay, so we're going to do both of the sides, right? So we're going to do this integral. I'm going to do this one first. I have to take the cross product. So I'm going to come over here in my different color and just say I'm going to do this part first. And to do that, I've got to take the cross. So I'm going to use my determinant kind of way of doing a cross product. So let's see. So remember, what we do is we put the unit vectors up here: x hat, y hat, and z hat. And then we put the derivative, the first thing in the cross product goes here. So that's del x, the components of del. And then we put the components of v. Now I'm going to write them as vx, vy, and vz. Notice that we really only have vy and vz. We don't have a vx. Okay, just because it's too messy to put them in there. Okay, and so I'm actually going to erase this vx because, hey, it's 0. Might as well just put it in as 0. Oh, come on. Okay, I'm gonna put it in as 0. Okay, so let's execute the determinant. Okay, so remember, the way that we do a determinant here is we scratch out this, we're scratching out this first thing and like this, and looking at this submatrix for the first thing, right? So it's x hat times that determinant of that submatrix. So that means del y acting on vz minus del z acting on vy, Okay, you got to be careful because there's derivatives. You got to keep that order. Okay, and then the next term has a negative sign. Okay, so let's get a different color for that. Okay, so the next term has a negative sign, so negative y hat. And then we're going to kind of scratch out this column, the middle column, and again the top row. And now we're looking at the submatrix. I'm going to write it down here in purple: del x, del z, 0, and vz. We're doing the determinant of that and putting it up here. So that's del x times vz. So del x acting on vz and del z acting on 0, which is just 0, right? Minus that. So, right, this would be del x acting on vz minus del z acting on 0. So that's just 0. So there we go. Okay, then the last one we have, get a nice bright color here. We're going to get rid, blocking out this last thing and the top row again. And we have plus z hat, and then we have the submatrix of del x, del y, 0 vy, the determinant of that, which is del x vy minus del y times 0, which is 0. Okay, good. So now we have all the pieces. Just making sure I did this right. Del x, yeah, okay. All right, so let's go back to our orangey color. Okay, I think that's our orangey color. There we go. All right, so now we just have to take the derivative. So let's see. The derivative with respect to y of vz is just 4z squared, okay? And then the derivative with respect to z of vy is just 2x. So minus 2x, and that's all in the x hat direction. Okay, here the derivative with respect to x of vz is 0. There is no x in vz, so we go minus 0, right? And then the derivative with respect to x of the vy is just 2z, so plus 2z in the z hat direction. Okay, so finally, right, we have 4z squared minus 2x in the x hat direction plus 2z. This is 2z in the z hat direction. Okay. Let me double check now. Let's double check. Let's see, I did this before. So yeah, it looks right to me. At least it matches what I did before. Okay, good. So now we have del cross v, and now we just need to dot it with dA for a surface. Okay, so what surface are we doing? I have to look and see what I said. What did I say? Oh yeah, over a surface of a square. So let's look. I'll show you. I'll show you what surface I'm talking about. So someone has to tell you the surface. It's not like you know, right? Someone got to tell you. It's not a known thing. So we're gonna do a surface. Here's our coordinate system again. This pen does not like to draw the diagonal. It's so weird. Okay, and then this is y, z, and x once more. And then our square that we have a surface that we're trying to do is, well, here, let's do that little orange color again. And we're going to do the surface, looks like this. It's a little square. And it has coordinates here of y equal 1 and z equal 1. Okay, so 1 by 1 little square. I'm sorry, I should have made more of my orange color go down here and here, right? Okay, and of course we have a surface that's the inside of that square. Okay, that's S. Okay, and this guy here is P. Okay, all right. So let's do it. So we have, so this is coming down here. So we have, oops, sorry, I meant to actually write an integral. Okay, so we're going to have the integral of our surface right, S of del cross V dot with dA, okay? And now we just have to think about what is dA, okay? Well, one, we have to decide on a direction for dA. Notice I told you it was arbitrary. It could either point in the positive X direction, right? So the dA, remember, is perpendicular to that surface here, right? It's perpendicular to the surface. It could either go in the X direction or the negative X direction, okay? Well, we decide here because we just decide which direction we're going to integrate the second integral over, right? So you may not always be integrating over the second integral, right? But in general, right, we're checking Stokes' theorem here, so that's why we are integrating over that as well as the integral over the surface. But you can pretend you are going to and just use right-hand rule. So if I take my hand and I curl in the direction that I want to integrate, then my thumb points in the direction of dA. So it's coming out towards me in the screen, right? So we're gonna have, I'm gonna put my little direction here, my direction arrows. Okay. So this is the way we're integrating around like this, counterclockwise. And so dA points, dA is, it's definitely in the positive X hat direction, okay? And it is dy times dz because nothing happens to x. So dy times dz. Okay, all right, fine. Also note that x is 0 the entire time we're integrating. So this term right here, I don't even need to worry about, right? I don't need to worry about that term. That's going to be 0 the whole time. Okay, so I don't need to worry about that. Okay, so I'm going to write this as the integral of 4z squared x hat. Oh, sorry. Hello. I didn't actually, I want to do the dot product before I do any of that. Hi. So notice that dA is in the x hat direction, which means that the only thing in the dot product that survives is the x component of the curl, which is here. Okay. And I already said x is 0, so it's only this 4z squared. So it's going to be the integral of 4z squared times dy dz, okay? And that is going to be the integral from 0 to 1 dz times the integral of, oh, hello. Yes, yet again, we got a problem. We gotta get that z over there. I meant to say dy there, okay. dy, because there's no y. And then the integral 0 to 1 of 4z squared dz, okay? Okay, so that's equal to this integral of 1, it's a y from 0 to 1, which is just 1. And then it's 4 thirds z cubed from 0 to 1, which is just 4 thirds. So this whole thing is 4 thirds. Okay, so this part is 4 thirds. Okay. All right, now we're going to do the other integral, the v dot dl around that curve. Okay, it's kind of a pain in the butt because it's got several pieces, right? But you know how to do path integrals. So what I'm going to do for this is I'm actually going to erase this because I want to keep this stuff up here and then get rid of this stuff down here, okay? So that's, oh no, what's happening here? Give me 1 second, I've got a little Zoom emergency. Okay, I don't know what you're talking about, Zoom. You seem to be still on. Okay. Shoot. Did I start the recording? No, yes, I did. Sorry, I'm having all kinds of issues today. All right. Let me erase. And unfortunately, I can't change the size of my eraser, so it's going to take me a tiny bit. Let me just erase. Yeah, oh, okay, this is very unhappy. Let me just erase all this. I'm going to pause the recording and come back. Okay, finally. All right, so now let's do the second one. Okay. All right, so we're going to do the integral over the closed path, P, of V, no, not del, V dot dl. Okay, all right, so we're going to have to pick which one of these we're going to do first. So let's do this side, I guess, right here. This side right here. Okay. And so, well, let's just write it out. So we're going to have the integral of d. Remember that, one more time. Let's calculate v dot dl first. Okay. So do that in the blue. So v dot dl. Remember, dl is this, is the same thing as dr, which is dxx hat plus dyyy hat plus dzz hat, okay? And so we have, this is going to be 2xz plus 3y squared in dy, right? Plus 4yz squared dz. There's no dx because there's no x component of v. Okay, it's fine. So this is going to be v dot dl, and we're going to integrate it over each side. All right, so we know we have to break up the sides. So let's break up the sides here. We have that one in the kind of a pinkish color. So that's, in that side, y goes from 0 to 1, x is 0, and z is 0. So let's look. X is 0, so this term's gone. Z is 0, so this term's gone, right? And so we just have 3y squared dy. So we have the integral from 0 to 1 of 3y squared dy, which is 3y cubed over 3 from 0 to 1, which is just 1. Okay, so that term, this is 1, okay? And let's do the next one in this blue color here. So we're going to do this guy. Okay, so in this one right here, right, is z goes from 0 to 1. Y is 1 the entire time, so I don't get any more y's, but my x is 0. Okay, so x here will be 0. Y doesn't go away, but dy doesn't change. So this term is going to not be there, right? Dy is 0. Y doesn't change. So I can get rid of this term. It's only going to be this term. So that's going to be the integral from 0 to 1 of 4yz squared dz, okay? And so that's going to be 4, and y is 1 all the time, so it's just going to be 4 times z cubed over 3 from 0 to 1, and that's just 4/3, okay? All right, so this guy over here is 4/3, okay? All right. And then we have yet another one here. Let's get a different color. We'll get a nice greeny green, and that'll be this guy here, okay? And so this is where y goes from 1 to 0, right? Z stays 1 and x is 0, okay? So y changes, z does not. Z is always 1 and x is 0. So we only have this term here. So we have the integral of 0 to 1 of 3, let's see, yeah, y. 3y squared dy, which is 3y cubed over 3 from, oh, not 0 to 1. Oh, that would have been a minus sign error. 1 to 0, 1 to 0, okay? From 1 to 0. So that means this is 0 minus 1. So we get minus 1. So this guy here is minus 1. And then we have the last one, okay, which is this one here. Okay, and in this one, z goes from 1 to 0. And y is 0 the whole time, and x is 0 the whole time. Okay, so what do we got here? dy is 0, so this term's out. Y is 0 the whole time, so this term is 0. So the integral from 1 to 0 of the term that survives here is the dz term, 4yz squared dz, but y is 0, so this is 0. Okay, so putting it all together in our blue color, we have the integral around the curve that bounds that square dot dl is equal to 1 plus 4/3 minus 1 plus 0 is equal to 4/3 as promised. Okay, all right, good. We've proved Stokes' theorem. Okay, yay, all right. Okay, we are going to go to a different lecture. So let me go grab that. I will pause the video. Okay, so let's move on. We only have a little bit left to go. So let's get another layer. All right. This one. Okay, so last thing we have to do is look at integration by parts. This is one of those things that is super useful in all of physics. So if you're like, wow, I haven't done that since calculus, you should refresh your memory. Okay, so let's take a look at just plain old regular integration by parts. Okay, so regular old integration by parts, we have the integral. So let me just start off with, if we have something like d dx of two functions of x, f and g. That should not be they're multiplied times each other. They're not with a comma. Okay, they're multiplied times each other. Then we use product rule. So we have df dx times g plus f times dg dx. Now let's imagine do an integral of all of this. Okay, what happens over here? I have to integrate everything dx, right? Okay, over here I have fundamental theorem of calculus now that tells me that this side here is equal to f times g at the boundary. I'll say I'm integrating from a to b. X equal a to x equal b. Right? This is just using a fundamental theorem of calculus, right? FTC. Okay. All right. So that is equal to these integrals, 0 to, a to b df dx times g dx plus the integral a to b of f dg dx dx. Okay. All right. So what this, if you look at the form of this, we have the derivative on one thing in the integral, that's the f, and then times that thing, that's the g, and then on the other integral here, we have the derivative of the g term, right? There's the g, times the f term. Okay, so the derivative of one thing times the other, and then plus the derivative of the other thing, right? The g1 times the first thing, right? The f. Okay. So, and that's equal to this boundary term. Now, why is that useful? Well, it's useful because a lot of times the boundary terms are easy to calculate, and sometimes they're 0. So sometimes, like in quantum mechanics, we see this be 0 in QM. This is 0. The boundary terms are 0. And that's just because we're usually integrating wave functions where f and g are wave functions, and wave functions go to zero at infinity, which is where we're usually integrating between minus infinity and infinity. Okay, and then what that allows you to do is you can say, okay, I want to take the derivative off of f and put it onto g. Well, that's easy. If this term is zero, then this integral, if I take the derivative off of f and put it on g, I just pick up a minus sign, basically. But don't worry about that. It doesn't even matter if it's zero or not. It just allows you to kind of switch up the integrals switch up the derivatives under the integral sign. You just have to pick up a boundary term and another integral, right? And that may not sound like the most exciting thing, but it is actually, okay? So usually you'll see it written like this. Let me go back to my orange color. You'll see it written like this: the integral a to b of g times the derivative of a function f dx is equal to minus the integral where you've changed the derivative, taken the derivative off of f and put it onto g. So dg dx times f dx plus the boundary terms. You'll see it written like that because it's often useful to take the derivative off of one thing and put it on the other. It might be that it's just easier to do the integral that way. All right, now we know that in vector calculus here, we are dealing with lots of vector derivatives, right? We have gradients, we have curls, we have divergences, and in fact, we have an integration by parts formula for all three of those things. Okay, so let's take a look at what those are. Real quick, I'm going to get another layer for this, actually. I need some room. Okay, so let's look, okay? Let's look at the divergence of some function of x. Well, it could be a function of x, y, z times a vector, okay? It's a scalar function times a vector function. Well, this turns out to be the function itself times del dot a, right? We've actually looked at this in our, when we looked at product rules. This is basically a product rule, right? Notice that our ordinary integration by parts started with a product rule, same idea, okay? Okay, so if we integrate this guy here, this here over volume, so let's integrate this over volume, del dot fa, and I'm not going to use the xyz in there, but yeah, okay, of fa d tau, we know by divergence theorem, well, first we know it's this, right? So let's write down, we know that this thing here is equal to all of this. So we have the integral over that volume of f del dot a d tau plus the integral over that volume of a dot the gradient of f d tau, okay? All right, fine. But we also know that this side here is, by divergence theorem, equal to the integral over the surface that bounds v, okay, of fa dot dA, okay? So this is equal to all of this, okay? This is that boundary term that we were talking about. So this is the boundary term, okay? So that means that this integration by parts here, the equivalent, right, is that we can write down, oh, I don't know why I erased that, is that we can write down this. We can write down that the integral of f del dot a d tau over that volume is equal to the change up the derivative, right? You take the derivative here is on a, you change it, put it on f, right? And you have to do that with a gradient, is the integral over that volume of a dot, negative that, because we're going to pull the other side, times the gradient of f, okay, d tau, and then plus the boundary term. Okay, so that's one of our integration by parts formulas. Okay, we're not going to go over all the other ones, but they're there for you to look at when you need them. Okay, but that's the spirit, right? That we have, you can take the derivative off of one part, put it on the other part, and get a boundary term for your trouble. It's the same idea for all of them. Okay, I think that's all we need right now. And I'll talk to you guys soon. In fact, tomorrow. Okay.